So we're presenting the paper at the KDD conference because we want to share some of the lessons we learned from applying machine learning in production at Google. When most people talk about machine learning, they only talk about the optimization algorithm or the model architecture. However, if you want to reliably deploy machine learning in production and at scale, you need to do much more than that. Let me give you an example. Even in the most basic production scenarios, you would want to make sure that your model does not train on corrupted data and that only high-quality models are actually pushed to production. Both of these validation steps are absolutely important to make sure that you avoid bad user experiences and service disruptions. So in the past, we built specialized systems for one learning algorithm at a time. Two of the most widely used systems at Google were specialized for large-scale linear models and deep neural networks. Today we use TensorFlow because it can solve all kinds of machine learning tasks in production. To take advantage of this flexibility, we built a brand new general-purpose machine learning platform, and we're calling it TensorFlow Extended, or TFX.
One of the first deployments of TFX was in the Google Play Store, where machine learning models are used to improve personalized recommendations for users. As new data arrives, new models need to be continuously trained and pushed into production. This kind of continuous training and serving is a common need of many Google-scale services and is well supported by TFX. When it comes to training, we want the best quality models using as little time and computational resources as possible. Now, when you have a large data set of hundreds of billions of examples, training a high-quality model from scratch can take a few days and lots of resources. But at the same time, many products like Google Play probably can't afford to wait a few days as they need fresh models to serve the latest content and user needs. So, one technique we found pretty useful for balancing this quality and resource trade-off is called warm starting, which means transferring a subset of model parameters, such as embeddings, from a previous model version. Warm starting allows models to converge to better quality faster with less resources. In addition to speed and quality, production-level reliability is just as important. And that's why TFX includes both data and model validation. In the Google Play deployment, we actually identify a feature skew between the training and serving time using the data validation components. And removing that skew alone led to a 2% increase in the app install rate. With model validation, TFX also makes sure that each new model passes a prediction quality bar, preventing issues like accidentally pushing partially trained models to serving because of system failures. Finally, TFX is also integrated with TensorFlow Serving, which allows the Google Play team to take advantage of serving optimizations, including batching, fast proto parsing, and minimizing resource contentions when serving multiple models.
So a general-purpose machine learning platform, such as TFX, needs to be easy to use and maintained by many different teams. To achieve this, TFX provides a unified configuration framework that allows our users to control the entire system end-to-end. In addition, almost all of our users rely on TensorFlow Estimators, a high-level API that implements the most common machine learning algorithms. Although we didn't focus much on the front-end tooling in our paper, it's a critical part of our platform. Among other things, our users are able to control and monitor the pipeline, visualize data statistics, and drill into model evaluation results. If you're interested in TFX, please go ahead and read our full paper, and parts of the TFX stack are also open sourced and available in the TensorFlow repository.